So, and use it using techniques that we are familiar with. But I want to go over some things that you can do with the data that we gave you. So I'm going to see, one of the pieces of data that I gave you was a data set on, it was called prediction of height or stature. Okay, and if you looked at the text file, I'm going to double click it so you can see it. Let me see if I can blow it up a little bit. You look at the text file. Uh, this is something that say, a archaeologist might use. And what they're doing here, or a forensic anthropologist might use, what they're doing here is they're looking at metacarpal length and they're using it to predict height. Okay, who knows what metacarpal is? Arm, wrist, this part, right? So a lot of times they'll find that part of a, if you're in a crime lab, they might find part of it. We just had an incident this week, right, where they found body parts all over New York and stuff like that. What's that? Hempstead, yeah. So, or actually, and I think a lot of towns actually, like it's kind of scattered around. So, or an anthropologist may find part of a very old fossil remains, and may want to predict what height is based on some body part that they frequently find. So, in this case, they took, I guess, what is this, about 8 or 10 instances where they were able to measure both height and metacarpal length, and they tried to see if there was a relationship between the two of them. So this is numerical data and numerical data. So what kind of analysis might we be doing on this? So what's that? Yeah, correlation, right? Numerical, we look at correlation, and we also look at regression. So in this case, a great thing for us to do would be to import it to SPSS. Well, you could do that in 2 steps. One step is to open the file in Excel. And I'm just going to drag it down here on top of Excel. I could have said, file open in Excel. I'm just going to drag it down there. And it opens in Excel. You can say open and locate the file from Excel, or you could just drag it on top of the icon. If I did it the other way, it would be File, Open, and I'm going to go to the desktop, and it was in Data, and from there it was in Prediction of Height, and there's stature.txt. I click on it. It makes me step through a few steps because it gives you a few options, but you can see if you just say next, 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 it just opens it up. Okay, now I can save that. I really want to work with it in SPSS. I'm going to say save as. Save it as change it from a text file. I'm going to say format for saving is going to be Excel workbook. I'm going to save it. Click save. I already did, so I'm not going to replace it, right? But you would say save. It saves it as an Excel file. So now from SPSS, if I open SPSS, I can say open data. Okay, open a data file, and it will open many kinds of data files. I'm going to navigate over to desktop, data, from data to prediction of height, and there's my actually. What you would see is you would see nothing highlighted there because you haven't saved it as a .sav file. But what we want, here's stature.txt and here's stature.xlsx, Excel file, right? What you can say is, I want to see Excel files. I want to be able to access Excel files. So I'm changing the file type from my open data in SPSS. So now I can click on stature.xls or XLS, depending on what version you have. Click open, and it asks me, I see data from A1 to B10. I'm guessing, it checks off, I'm guessing that the top line is the variable name. It's not really data, it's just a name. And it was metacarp, and I forget what it was, height, metacarpal height or length or something like that. So I'm going to leave that checked so it doesn't think that's data, and it uses that variable name that's at the top of that file. And sure enough, it allows me to open the file in SPSS. Right now it opened in the variable view. It recognized that they were both numerical variables, scalar. It grabbed the name, metacarp, and stature, and If I go back to the data view, I can see they're listed there. Okay, those are my heights. So what's the first thing I might do with numerical data if I want to show a correlation? What's that? Scatter plot, right? Let's take a look at this data on a graph. So I'm going to go up to graphs. I'm recording this, by the way. I'm going to go up to graphs, legacy dialogues I like to use because it's simple, scatter dot, simple scatter dot, and just tell it, well, in the x-axis, I'm going to put metacarp. In the y-axis, I'm going to put y-axis. For the purposes of correlation, it doesn't matter which one you put where. For the purposes of regression, where you're going to use one to predict another, you would use the one that's the independent variable, right? The one that you want to use to predict the other in the x-axis. That's the predictor variable or independent variable, and you put the dependent variable, the one that you want to have it predict, or dependent variable in the y-axis, and that would be metacarp. So I'm gonna do that now, just to avoid having to worry about it. If you want to dress it up, you can click titles and put a title in here for your graph because you want to use it in your presentation and so on and so forth. I'm not going to bother with that for now. I'm going to click OK, and it'll produce the scatter plot for me. So you take a look at it. You say to yourself, does that look like there's a correlation? So how about you guys? Do you think that looks like there's a correlation? Right? As the metacarpal length goes up, what happens to the stature or height? Goes up also. In fact, I can ask it to draw me a line. I'm going to double click in here, and a window comes up, lets me edit this window. And if you look at this little one right here, this little add fit line at total, that one right, if you just click on that, it'll add a line that approximates our line of regression. In fact, it even actually calculates an R square. Right? See that little R square up there? Right? That R square was the correlation squared. R is the Pearson's correlation. R squared, it's 73.73 or 73%. Anybody remember what R squared tells us about a correlation? What does that tell us roughly about a correlation? In other words, you guys online also, what does that R squared tell us about a correlation? If that correlation were 90%, what would it be telling you? It would be telling you that 90% of the variability of the variability in the dependent variable is caused by the value of the dependent variable. Margaret got it right. Great, good work, Margaret. So that's pretty good. That means only 25% is due to some other variables that we don't see here. So this is a pretty good predictor, right? It's good correlation, a pretty good predictor. So this is one thing we have. We have our chart. We can click on. I'm going to click on this. I can copy it into my presentation and so on and so forth. What I can also do is I can actually calculate, analyze, and correlate and regression are down here. Bivariate correlation because it's two values. And since it doesn't matter which one goes in first, there's only one box there. Pearson's correlation. I'm going to click OK. And it actually calculates this for me. And it finds that the Pearson's correlation is 0.856. That's R. So R squared is going to be 0.856 times 0.856. That's an excellent correlation. Anybody remember what a perfect correlation is? 1, right? No correlation at all is 0. Exactly. No is 0. And a perfect correlation is 1. Okay, so this is a really good correlation. And we also know that we can say with confidence, with statistical significance, that it's different than 0, right? There is a correlation. It's different than 0 because we see this significance here. Next thing I might want to do, I can put this into my report as a correlation to demonstrate that there is a significant correlation, and it's a very good one. I can then go into regression and actually do a linear regression. I'm going to regression linear, and this time my independent variable is going to be metacarpal. It's going to matter now, and my dependent variable is going to be stature. I want the metacarpal length to predict the height that person's stature or height when they were alive. Let's say if it's a very old fossil. So now I can click OK. And now SPSS will do our calculation for us. Sure enough, there's our R square, it's 0.733. It does our analysis of variance. This tells us that this is a significant result. That's what we saw. That 0.003 is the probability that our null hypothesis would be that there is no correlation between these two variables. Our alternative is that there is. And since this came out to be less than 0.05, we reject that null hypothesis. Now, it also gives us a box which gives us coefficients. You guys remember what the coefficients were for? They were for a formula for a straight line that would describe the relationship between these two variables. I'm going to get my graphics tablet so I can draw this. Yep. Come on. It goes that way. There we go. Okay. And let me get my notebook up. Okay. Boy, it seems like every time I try and open something, 9 things want to update. But, okay, let's take a look at this. Now, I'm going to try and get both of these up here at the same time so I can work with them. So my formula for regression is going to be y is equal to alpha plus a beta. Let me get this out of my way. There's something there you couldn't see that was in my way, plus beta x. Beta is the slope, alpha is the y-intercept. So y is going to be equal to some coefficient which represents the y-intercept. That's going to be my constant, that 94. Okay, I'm going to round it off to 94 just for our purposes. Plus beta, which is the slope, and that's the rate at which the metacarpal, that the height increases for any increase in metacarpal. In other words, for every one increase in metacarpal, the height increases 1.7. I guess that's, what is that, centimeters or millimeters? Centimeters, right? I guess the heights that they're talking about here are centimeters, plus 1.7 times x. Okay, that formula now is the formula for this straight line that we drew when we drew that regression, with that correlation scatter plot. Okay, so that number, that's what this represents. This formula now can be used as a predictor for height. For instance, if I go back here, the metacarpal length was 41, 39, 54. Nobody here has a 50 millimeter, maybe one's millimeters, the other centimeters. I don't know what the units are here. These must be centimeters, I would think, right? 2.5 centimeters to an inch. So these would be reasonable heights in centimeters. Metacarpal length, that seems big for, that's 45, be about 10. I guess that would be right, centimeters for both. Okay, so at any rate, so I don't see one that's 50, right? So let's say I find a new fossil and the metacarpal length is 50. I want to predict what the stature, what the height of that person was. So now I would use this formula. I just plug in 50 for x. So y, or the height, is equal to 94 plus 1.7 times 50. And that would come out to be 1.7 times 50 plus 94. That would be equal to 179. Okay, so now I'm going to show you something that we can do with that. Hang on, before we do go any further. Divided by 2.5 equal, that's right. So that's inches probably. This person would be like a little under 6 feet tall, I guess. Okay. So at any rate, so we can use that formula as a predictor, right? Now you might have noticed that when we drew the graph, that only one point was exactly on that line. In other words, that formula, although it was a good estimator of height from metacarpal length, that formula was not perfect except for one particular individual, right? So I can actually go back and I can actually predict, I can actually estimate how far off each one of these people were, each one of these measurements were. And the way I would do that is I would go back, and you don't necessarily have to do this, right? But I could go back to analyze, but you might be interested in it, analyze, regression, linear, and go into save and check off residuals, predicted values, and unstandardized residuals. I'm going to click continue and say, okay, it's going to do the same analysis it did before, except this time, in addition to doing exactly the same analysis that it did before with the same results, if I go in here to, let me find it, let me find my data file again. Let's see, my data file is here. If I go into my data file, got the wrong data file. If I go into my data file again, it gave me two new variables. Remember we only had two variables, metacarpal and stature. It created two new ones. And that's predicted value, unstandardized predicted value, and the other one is unstandardized residual. Okay, what this is the number that we would get if we plugged 45 in for X, and this would be what we would find for Y. If we plugged 51 in for X, this is what we would find for Y. And this column over here is the difference between what we would have predicted using the formula and what we would have found using the and what the actual length for that person was that we actually measured, right? And that's the difference right there. That residual is our error, basically. Okay, this we want to know because we want to make sure that at the low end of metacarpal lengths, that we're not always underestimating, at the high end, not always overestimating, or vice versa. We want to know that these errors are random. Sometimes they're high, sometimes they're low, but they're random, so there's no pattern to them. Okay, that's important to us because it would suggest that there's something wrong with our linear relationship if those errors weren't random. Okay, so that's one of the things you might look at it, if you were really doing this in depth. That might be a little bit beyond what we want to do for this. So what does this all mean for you? What it means for you, if you're really desperate, you might take this particular data set and use this particular data set, but hopefully that would inspire you to go to one of the data sets that we have that has some numerical variables in it. For instance, one of the ones that I put up a full data set for the New York City Health Survey, but more recently, I put up one that I called New York City Community Health Survey Reduced Variables. I didn't reduce it that much. There's still 50 or so variables, right? But you may notice that the first 9 or 10 of them are all linear variables. I think this is a linear variable. What is this? Thinking about nutrition, total servings of yeah, that one's a linear variable too. I don't know why it said that. I think it is. We'll take a look at it when I go back. Let me just take a quick look now. Oh no, maybe it is. No, it is. It is a numerical variable. Okay. So at any rate, these kind of the names are kind of funky, right? It's really the questions. It's really the label that gives you information about this, not so much the names. Okay, so let's say I want to do this with a couple of these variables. Well, let's see. I got BMI here, right? Maybe I can relate BMI to the number of 12-ounce sodas consumed per day. It's standardized, continuous variable, standardized to per day. In other words, probably ask people how many sodas you drink in a week or a month, and then they just changed it to divided by the number of days or something like that. So if you look at these two variables, BMI and NS, number of sodas day per, okay. Okay, well, BMI is just BMI. It's a number, right? Two-digit number, 0.2, 30, 22, and so on and so forth. We're familiar with that. Number of sodas per day is this number here. And you'll notice that a lot of zeros and there's ones and so on and so forth. So you may find some people with more or some people with less. Number of sugary drinks per day, number of sugary drinks per day, standardized, so on and so forth. Number of sugary drinks per day, average, is that what that is? Let's see if we go back to that variable view. Oh, number of cigarettes smoked, okay, per day. So let's say I want to see if there's a correlation between these two variables. I'm going to go first, take a look at it on a graph, scatter dot, okay, define, and I'm going to move BMI into, say, the y-axis. I'm thinking number of sugary drinks per day might be a predictor of BMI, maybe. I'm going to move that in there. Number of 12-ounce sugary drinks. Number of sweetened, let's see, number of sodas plus sweetened drinks per day. I'm going to use that one. Number of sodas plus sweetened drinks per day. I'm going to click OK. Okay, let's see what our scatter plot looks like. Yep, there it goes. Well, kind of looks a little funky because there's so many people that don't drink any or drinks very little soda per day. There's some people that drink 20 per day. That seems a little weird, right? But that's up to them. Okay, I'm gonna see if I got a line and see what direction it goes. Well, that line tends to go upwards a little bit, doesn't it? Seems like based on the number of sugary drinks you drink per day, your BMI might be higher. Let's see if I can if there's a linear regression I can tease out of this. And one of the things I might consider doing is maybe eliminating all the zeros here or something like that. Analyze, scripted statistics. Let's see, where am I? Correlation. Let's see if I get any correlation at all. Body mass index. Sodas. Number of sodas plus sweetened drinks per day. Okay, let's see if I get anything. Okay, well, I could come pretty close to getting a correlation. I get a correlation, its significance, but it isn't very good correlation. That's very close to zero, right? It's significant. It's different than zero, but there's not much impact, it seems like, on BMI. So, like, in other words, there are many other factors. If we squared that, it would be even a smaller number. So there's many, many other factors that seem to affect BMI other than just soda, as we could predict, other than just soda consumption or sugary drink consumption. So maybe this isn't a great one, but you can play around with them a little bit. What we have many more of here than numerical variables is you have many more categorical variables. For instance, we have marital status. We have gender, we have ethnicity, we have whether or not a person's been diagnosed with, been told they have asthma in the last year, whether they've been told they have diabetes in the last year, whether or not they've had an HIV test in the last year. We have information about their employment status and so on and so forth. Let's take a look at a couple of these categorical variables. Employment status, 3 categories. Let's see what the categories are. If I go over here to values, if I click in there, it tells me, well, the 3 categories are employed, unemployed, or not in the labor force, not looking for a job or for whatever reason, not in the labor force. So I have 3 categories there. Okay, well, how about educational status? Okay, well, let's see what kind of categories they got there. Less than high school, some college, and college graduate. Well, let's see if there's an association between your educational status and your employment status. Okay, categorical, categorical. What kind of analysis do I do if I have two categorical variables? Where do I start? What's that? First, I want to get a look. I want to get a look at the numbers first, so I go for crosstabs. Okay, everybody remembers this, right? This is not anything new. Crosstabs, right? So I'm going to give that a try. So you guys remember for me that the variable names are education and employment, M3, education and M3. So I'm going to go to my data view. I'm going to analyze. I'm going to go to descriptive statistics and crosstabs. And I'm going to say that I'm going to guess that educational, the amount of education is going to affect employment. So I'm going to put the exposure into the rows and the outcome into the columns. So the exposure in this sense is going to be education, the amount of education you have, and the outcome is going to be whether you're employed or not. So let's see. I am going to move, what was it again? Education was just educate. Oh, look, we don't even have variable names. We just have education status. Okay, I'm going to put that in the rows. And, oh, I'm sorry. Yeah, I was going to put that in the columns. And, no, I had it right. Yeah, I was going to put that in the rows. And what was it? It was employment status. Oh, oh, you're right. Got it in the columns. And education was the one I wanted to put into the rows. Yeah. Well, remember we're saying that education is going to impact whether or not you're employed or not. That's our presumption. So the independent is education, dependent is employment. But I'm looking at it as a cross-step, like exposure and outcome. Okay, so I'm going to put that in there. I could try marital status next. So I'm going to ask it to, right now, I'm not going to ask it to do any statistics. I'm going to not check anything. I'm not going to ask it to do any statistics yet. I'm going to go into cells and I'm going to tell it, just give me the observed values. Just give me that table. Click OK. Let's see what I see here. Well, less than high school, there's 439 people who are employed out of 1,377. High school, 886 out of 1,806. It's kind of hard to see because of the size of these numbers, kind of hard to see if there really is an impact of education on employment. So I'm going to go back to Analyze, Descriptive Statistics, Crosstabs. I'm ignoring you guys online for a few moments. I'll get to you. And I'm going to go into cells, and this time I'm going to tell me, give me the percentages by rows. So it's going to now calculate the percentage of people out of the total for each row that are employed or unemployed for that matter. And I'm going to click OK. Okay, and this time we get a little bit more information. Well, if you're less than a high school diploma, 31% of those people in the survey were employed. High school graduate, 45 were employed. Some college, 53% were employed. College graduate, 67% were employed. Master's degree in public health, 99% were employed. Right? We don't see that column. That column's not on this. They weren't part of that survey. So at any rate, so we see that there is a relationship here. We see literally as the level of employment, level of education goes up, the level of employment goes up also. This is an interesting result for us, isn't it? Okay? So this is something that might be useful. Marital status. You can check marital status against employment. You can check education against marital status. If you have more education, you're more likely to be married, for instance. There's a lot of ways you could manipulate this data. If you're having trouble with it, pick something out that you think is interesting that might be productive. Okay? And if you're having problems with it, email me and I'll help you out. A word of warning. I'm tied up tomorrow night and from about 7 till about 11. So there'll be a window there where I can't answer emails. I can't get the email and stuff like that. And she who must be obeyed, my wife, says that I have to have that period of time. So I won't be able to answer emails in that period of time. But any other, I tend to stay up late, so I'll be available after that. Most likely. Yeah, I know how that's going to go. So at any rate, Okay, I got a question here. What if you get a chi-square result that's really large, 100 plus, with corresponding p-value of, Nicole, that would indicate that there really is a difference between what you would have expected. In other words, if I look at the employment status here, overall, if you look down here at count at the bottom, 54% of everybody they surveyed was employed, right? If if there was no relationship between educational status and and employment, I would have expected to see each one of these categories instead of 31, that be 54% of those people employed, 54%. It would all be the same. That would be our expected values, would give us all the same percentages, right? Since the percentages are different, right? Since these numbers are different, giving us different percentages than what we would have expected. Matter of fact, let's do that. Analyze, descriptive statistics, crosstabs, and this time I'll ask it, give me expected values. This time I'm going to turn off percentages just so I can get a look at just that. So it's not confusing, a little less confusing. Okay, if I look at that, well, the actual, when I had 1,377 people, if everybody was unemployed at the same rate in all four rows here, overall 54%, if I surveyed 1,377 people who had less than a high school education, I would have expected that 747 of those 1,307 would be employed. In fact, only 439, right? So that difference in this box and the difference in the unemployed box and the difference in the high schools and so on and so forth, all these differences add up to giving you a bigger chi-square number and a lower p-value. So if those differences are small, your chi-square value is small, right? And you get a high p-value, you can't reject your null hypothesis that there is an association between educational status and employment status. Now, one of the sloppy things about this is, got this extra column here, so not in the labor force. I really don't like that very much, right? Because it's so nebulous. Why are they not in the labor force? Are they sick? Are they retired? And so on and so forth. We don't know. So I would love to get rid of that column, right? That would really be nice. So I'm not saying you necessarily have to do this. If you're uncomfortable with this, you can either email me and I'll help you with it, or you can ignore it for the time being. But what I would love to do is go back to this data. And one of the things, once you settle on something, like right now, I know what I want to do with this data set. So what I might say to myself is, I'm only using two of these columns. So that column up to, all the way up to employment, was it? Employment 3, all the way up to this column, I'll say clear those. Get rid of them. Oops. Okay, and I'm only using, did I get rid of my other one too? I think I did. I'll undo. Employment and what else? Employment and education, right? There's education, okay, good. There's education as employment. So I'm going to highlight that one. I'm going to hold down the shift key, go all the way back to here, clear all of these. And then I'm going to go over here and I'm going to say, I'm not using that one. So I'm going to clear that one. And I'm not using any of these others here. So I'm going to clear all those. Now you might keep marital status or some one of the others. So now I only have two variables, right? So much easier when I go into descriptive statistics crosstabs. I only see two variables to decide what to do with, right? Just makes it easier for me. Okay, so now one of the issues I just had was under employment, we had that extra category, right? I'm going to go to variable view, okay, and I'm going to click in here, and it tells me, well, a 1 was employed, a 2 was unemployed, and 3 was not in the labor force. I want to get rid of that 3. I'm going to show you two quick ways to get rid of that 3. The good way to get rid of that 3 would be to create a new variable. Okay, I'm going to say data, I'm going to say transform, recode into different variables. And I'm going to say, I want to take employment status, right? And I'm going to start with employment status. I'm going to change it into a new variable, employment 2. This employment 3A, right? It was employment 3A before. Okay. And now it might be employed, the label might be employed or not employed, right? That's, and my variable name is going to be emp3A. Okay, now what I'm going to say is, what I want you to do, SPSS, if that value is a 1, that meant employed, remember? Make the new value a 1 also and add it. Okay? If the old value was a 2, make the new value a 2 and add it. Now, what's it going to do with 3? I didn't tell it what to do with 3. It's going to do nothing with 3. So it's not going to copy over the variable 3. And I'm going to say, okay, that looks good to me. Go ahead and change it. Make the new variable and say okay. So now it actually created a new variable. Here's our new variable. If employment was 1, then it's 1 in employee 3A. 2, but the 3s it didn't copy over. They're just not there. Okay, and what you need to go back now is you got to go back in here because it didn't copy over the values and remind it that 1 meant employed and 2 meant unemployed. Okay? Okay, so now I'm going to go back and do my analysis again, except I'm going to use that new variable. Descriptive statistics, crosstabs, okay, and instead of using employment status, I'm going to use my new employment status, employed or not employed, and I'm going to say, what did I do here? I'm going to do percentages by rows and expected and observed. Actually, I'm going to turn off expected, just percentages by rows. Say okay, and there we go. This now is, you'll see it's still 73% because it was ignored. No, actually, it's higher now. It was a much lower numbers, but now it's only considering people that want to be part of the labor force. But we still see that kind of almost like dose response relationship here, where as the educational level goes up, uniformly we see an increase each time you get more education. There's a higher likelihood that person's employed if they want to be, if they're in the labor force, right? So we see that relationship. That's very helpful. Chi-square is going to be, if I want to run my chi-square, that's going to work out, as well, and so on and so forth. Now, one of the other things I might want to do is I might want to do, I might want to reduce this to 2 categories, compare less than high school to everybody else. If I only do 2 categories, make a new variable, only do 2 categories, I can then do odds ratio. You can only do odds ratio relative risk if you have a 2x2 table. Okay, I'm not going to get into that now. Okay, but I can help you if you want to do a 2x2 table. I'll help you with that if you send me the data, and I'll work with you on it as best I can, as much time as we have for this that's left. Okay, so that's how we would deal with categorical variables. Okay, you have a ton of categorical variables there. You can play around with, you can choose which ones you want and trim down the data set, and then you can work on your individual project and research